What we've done so far is we've looked at charge moving inside an external magnetic field and the forces that are exerted on that charge. In this section, what we're going to do is we're going to talk about the magnetic field that is produced by charges, produced by moving charges specifically. And we're going to do that, and we're going to use some analogies here. Let's go back in electrostatics to this equation right here. That's the magnitude of the electric field due to a point charge. Now, for continuous charge distributions, like a line of charge or a surface of charge, we broke that into charge elements, dq, and each produce an electric field, dE, so that dE is 1 over 4 pi epsilon naught dq over r squared. So that was the magnitude of a differential charge element. There's no direction associated with that. So you can imagine, here's some random charge. We'll break up into a little small segment. That would be a dq right there, dq. And then out here, some distance away, let's call that distance r. Then at that point P, there would be an electric field that is due to that. And then we would sum up over the entire surface here to figure out what the total electric field was at that point right there. Okay, so that should be review. These two equations here, though, there is no direction component. In order to figure out the direction of the electric field at that point, we had to rely upon other means. And typically, that was just the recognition that, for positive charges, electric fields emanate away from it. For negative charges, electric fields terminate on the charge itself. Well, it is possible to take these and include some directional information there. And the hint is right here to how to do that. You see this vector coming off of here. I called that a distance, and it is a distance r. But if we treat that r as if it is a vector, then we can write this dE as 1 over 4 pi epsilon naught dq over r squared multiplied by a unit vector that's in the direction of r. So the unit vector would have a magnitude of 1. So when you multiply, it doesn't change anything about this. But the direction of r hat here is in the direction of r. So we could write it that way. We could also write it this way, though. When we do that, then this becomes a vector equation there. If we change it up a little bit, we could also write the vector equation this way. 1 over 4 pi epsilon naught dq over r cubed multiplied by vector r. So we just changed this. We multiplied by r over r, and r is the magnitude of this vector here. In other words, it's the distance away from that dq to that point. So what we have right here becomes this vector r, the magnitude multiplied by the direction. Then down here on bottom, we end up with r cubed. So this is just another way to write what you already know, the electric field due to a point charge here. And it includes now directional information. So you see there's an r cubed on bottom, but it cancels, so this is still an inverse square law, just like we've always known before. If we treat r as a vector then. By analogy, we're going to do the same sort of thing for magnetics. And here's the way to think about that. Let's just divide up the page here. This will be the electrostatic portion, and now we're going to talk about magnetics over here. Let's say that we have a wire, a current-carrying wire that's in some shape. Let's say like that. And we've got a current going in that direction into the wire that's I. Well, let's take some little section of the wire, and we'll break it up into tiny little sections, the same way that we break this surface up into tiny little sections here to add up all the charges. But we'll break this current-carrying wire up into a little section, and we'll call that ds. And ds we'll treat like a vector. ds points in the direction of the current, but its magnitude is just that differential length there. And then we'll go out from ds out this way. So from there out here. So the ds vector points that direction inside the wire. And this is a vector we'll call r. And at this point out here, which we'll call point P, there is a magnetic field, which we'll call dB, that is due to this current carrying wire here. Now, we're just stating that without any proof whatsoever at this stage, but a current carrying wire produces a magnetic field out here on this side at that point P. Now that dot there does not indicate any sort of direction. That's just the end of the arrow there. Well, what is dB at P? Well, has been found that dB is equal to mu naught over 4 pi times I ds sine of theta divided by r squared. Now this is something called the Biot-Savart law, written in its magnitude form. The way you'd spell that is Biot-Savart. And a law, hopefully you recall, is empirically derived. So this is derived from experiment, not from first principles here. So we've got this angle between the ds vector and the r vector, which we'll call theta. That's this theta down here. The r is this length, the distance away from that segment of the wire out to the point P. And of course dB is the magnitude of the magnetic field at that point due to the current carrying wire here. There's a problem here though. There's a couple of things that, well, maybe you don't recognize this term, mu naught. Mu naught is the permeability constant. So mu naught is actually equal to 4 pi times 10 to the negative 7th, and the units are Tesla meter per ampere. That's what mu naught is, and it's called the permeability constant. It plays the same role in magnetism as epsilon naught did for electricity over here. If you want to spell that, it's permeability, P-E-R-M-E-A-B-I-L-I-T-Y, permeability constant. And the subscript 0 means that it's the permeability of free space, which is an old-fashioned word for vacuum. Do this multiplication, and it turns out that that's approximately equal to 1.26 times 10 to the minus 7th Tesla meter per ampere. Okay, so that's what that is there. Now, let's use this form here to determine what the magnetic field is at a point due to a current carrying wire. What we would have to do is we would have to divide the wire up into little segments, and then we would have to sum up all of those segments here. Now, it would be difficult if the wire were bent weird, some weird shape like this one here, but we can do it for a more straightforward problem. Let's take a straight wire here, an infinitely long straight wire, and then some point out here. Let's just call that point P right there, and it's a distance r away from the wire, so that distance there, let's call that big R, and the wire is carrying a current I in it. So we've got this straight, very long wire carrying current I, and the question is, what is B? What is the magnetic field, a distance r away from the wire, perpendicular to the wire like that? We solve this kind of problem then by dividing the wire up into differential length segments, ds, and then summing up over the entire length here. So let's choose an arbitrary length segment. Let's call that length segment right there ds. The direction is going to be in the direction of the current. and then the distance to this point here is little r. Now little r is going to change. As we integrate up and down this wire here, you know that little r is going to change. When it is right here, it's going to be exactly equal to big R. But it gets longer up this direction, it gets longer down in this direction. All right, so let's call the distance that we are away from this center point here, let's call that distance S. And we're calling it S from there to there because we've called this differential segment ds. All right, now we need an angle here. The angle between the ds vector and this, which we'll call the r vector, we're going to treat it like it's a vector, like we discussed up here. So the little r is a vector. We need an angle between those two, and that angle there is theta. All right, I want you to notice that we've got a triangle here. And if that angle there is theta, then this angle right here is pi minus theta. Okay, that's that interior angle of the triangle there. All right, so the magnitude of the differential magnetic field at that point is given by this equation here. dB equals mu naught over 4 pi times I ds sine of theta divided by r squared. So that comes about from what is affectionately known as the BS law. All right, so we could figure that out from that. So let's go ahead and do that, because what we want to do is we want to figure out what is the total magnetic field B, and that's going to be equal to the integral from negative infinity to positive infinity of all of the individual dBs, like that. And it's going to be equal to, since this is going to be an even function, in other words, whatever we get going from 0 to infinity in the positive direction is going to be doubled from 0 to negative infinity down here. So we could write this as 2 times the integral from 0 to infinity of all of the individual dBs. There. Okay, let's plug this in. Integral from 0 to infinity of mu naught over 4 pi, those are constants, times I ds sine of theta over r squared. Okay, there are three variables here though. Theta is going to change as we integrate up and down this length here. Theta is going to change. S is also going to change. The big S here, the S, not the ds, but the S is going to change as we increase up the path there. And also R is going to change, this R, obviously as we get farther up. Okay, so we've got those three variables here, but those three variables are related to each other. And I'm going to move this up and get another sheet of paper, because I want you to see how they're related to each other. They're related to each other through this relationship. The sine of pi minus theta, in other words, this angle right here, is equal to big R over little r. Okay, so this is the opposite from our angle, pi minus theta. It's the opposite over the hypotenuse. So that's what that is. But it's not so obvious, but this is indeed the case, that that is also equal to sine of theta. Okay, so the sine of this angle here is the same as the sine of that angle there. If you don't believe me, just try it. You'll convince yourself. All right, now there's a relationship then between big R. Big R is a constant. It's not going to change. But the little r is definitely going to change. So we could rewrite that ratio as big R over, and little r is the hypotenuse here, the square root of s squared plus big R squared. All right, so that's the sine. In other words, we can take this and substitute it in up here. All right, let's go ahead and do that. we're going to skip down here, and b is equal to 2, I'm just rewriting it at this point, times the integral of mu naught over 4 pi times I ds over r squared, and now I'm going to plug this in, r, big R, over the square root of s squared plus big R squared. Okay, now that puts us on this sheet of paper. Okay, now ds is what we're going to integrate over. So s is a variable, but r here is still also the variable. What we need to do is we need to substitute in for that as well, and you already know that that's r squared, and from our little triangle here, r squared is just going to be s squared plus big R squared. So when we do that, we end up with 2 integral 0 to infinity mu naught over 4 pi I ds big R over, and now this is going to be what's inside the under the radical here, so it's going to be s squared plus big R squared raised to the 3/2 power. 1/2 for what's on this side, and then squared for what's right here. Okay, so there you have it. This is something now that we will be able to integrate. So the total b is going to be, let's factor out everything that's a constant here. The 2 is a constant, the mu naught is a constant, the 4 pi on bottom is a constant, I is a constant, and what have we got left? From 0 to infinity of big R over s squared plus R squared to the 3/2 power times ds. Okay, now this is the type of integral that you should be able to complete. I left the big R in there because it's also on bottom here, and if you go to an integral table and you look it up, oftentimes you'll find it in this form right here. Okay, when you integrate this, I'm not going to work the integral, I'm going to jump straight to the solution, but when you integrate it, you end up with this, mu naught I over 2 pi big R, that comes out of the integration, multiplied by s over s squared plus big R squared to the 1/2 power, and now you evaluate that from 0 to infinity. All right, you have to do a limit in order to accomplish this. You can do that, and when you finish it up, here's what you end up with: mu naught I over 2 pi R. There. That is what the magnetic field, that's the magnitude of the magnetic field, a distance big R away from a long current carrying wire. So as long as you're not too close to the ends here, that's what the magnetic field magnitude is, a distance R away from a straight wire. All right, so there you have it. Now here's an issue. This is the magnitude. It does not include direction information. So in a sense, that's very much like what we were back here. We had to do a little trick, a little algebra trick to include this. And as long as we have a positive dq, the electric field is going to point away. But if dq is negative, then the electric field points inward, which is exactly what you expect. For a positive charge, electric field lines point outward. For a negative charge, electric field lines point inward. So how can we take this and how can we get direction information out of it? Well, here's the idea. The form of the equation that we have is this. This ds we've treated like a vector already. R is also a vector. We can treat that like a vector as well. So perhaps we can play some tricks here in order to get some direction information out of this. And you can. I'll just tell you what it is. In vector notation, dB is equal to mu naught over 4 pi times I ds vector cross R vector divided by R cubed. This is the BS law right there. Okay. Now, this will give us the direction information for dB because we have the cross product here. The sign is part of that cross product here. So we added the R here, and then we added an R down here. So we effectively multiplied by 1 by doing that. The sign was absorbed then into this cross product. All right, so that allows us to figure out the direction information. So how do we do that? Well, cross products mean you have a right-hand rule. So how do we figure out direction then? Well, the BS law is mu naught over 4 pi I ds cross r over r cubed. That's the BS law. The direction is from the cross product up here. So let's imagine that we've got a long straight wire here. This is our long straight wire, and it is carrying a current I upwards in that direction, just like that. Then over here on the right hand side, let's say a distance out here of big R. We want to know what is the direction at that point right there. Well, ds is in that direction. It's in the direction of the current. And then r, the vector little r, is in that direction right there. That's little r. So ds cross r, that means that's into the plane of the paper. So over here, what does that mean? That means that the magnetic field at that point is into the paper. And we got that from the cross product. So dB is down into the paper. And now if you do that same sort of thing over here on the right hand side of the wire, you end up with the same answer. Go ahead, see if you can do that, but you should come up with into the paper for every point over here on the right hand side. What about on the left hand side now? From over here, a distance r away. Well, ds is still in the same direction. This is little r. So over here on this side of the wire, ds cross r, you see my thumb points up. So this is out of the paper. And over here on this side, regardless of where you're at, you're going to see the same sort of thing. The magnetic field is pointing up out of the paper over here on the left. All right, so you've got into the page over here, out of the page over here. What about above the wire? What about in this section? Well, you can think this through, and you will discover that above the wire, the magnetic field points in that direction. The tip of the pen represents the tip of the arrow, so the magnetic field is going in that direction. Below the wire, the same sort of thing, except it's going in the opposite direction. So what have we got here? We've got a magnetic field that actually encircles the wire itself. If I were to look at it from the end, let's say this is the end of the wire. I'm looking at it from down here. And the current is going into that direction right there. All right, so what about over here on the right-hand side? Well, magnetic field is going down. Over here on the left-hand side, magnetic field is coming up. Above the wire, magnetic field is going that way. Below the wire, magnetic field is going that way. So do you see what we've got? We have encircling the wire, the magnetic field going in that direction. So that would represent an equal magnitude anywhere along that circle. We'll have an equal magnitude along that one. We'll have an equal magnitude along that one. But the magnetic field direction is the same in all of those. So you determine the direction of the magnetic field then from the cross product in the BS law. In this case, the magnetic field lines are concentric circles, and if the current is going into the board, the direction of the magnetic field lines are going to be clockwise, concentric circles. If the current was coming out, well, they would also be concentric circles, but they would be going the other direction then. All right, so it is this interaction, these magnetic fields interact with the external magnetic fields coming from, say, another source, and those create then forces. It's the interaction of the magnetic field intrinsic to the wire to the magnetic field that's coming from another source, the external magnetic field. The interaction of those two magnetic fields then cause the wire to experience a force. So let's use that bit of information then, and let's talk about a problem. Let's begin and say that we have two parallel wires here. Here are my two wires. And let's call this wire A, and this will be wire B. And we've got a current going in this end of the wire that's I sub A. And let's say we've got another current going in this direction, and that's I sub B. So we've got these two parallel wires, and they have parallel currents. If one of those currents was going the opposite direction, we would just say that's an anti-parallel current. Okay? But they happen to be parallel in this case. Now, each of these wires, because they have current going through them, are going to produce a magnetic field. All right. The strength of that magnetic field, let's talk about the magnetic field due to A, is going to be mu naught I sub A over the distance away, 2 pi times the distance. And let's say the distance between these wires here is D. So the magnetic field caused by wire A at the distance away that wire B is going to be given by this quantity here. And vice versa, if I wanted to know what the magnitude of the magnetic field due to wire B is, it's going to be mu naught I sub B over 2 pi D, like that. So what I'm trying to say is this wire creates a magnetic field that encircles the wire, and over here on this side of it, a distance D away, there's a magnetic field. Okay, well, what's the direction of that magnetic field over here? The direction of that magnetic field is going to be in that direction, and that's going to be the case all along this wire. So this is B sub A. It's going into the page here. How do I know that? Grab the wire, put your thumb in the direction of the current, your fingers naturally curl in the direction of the magnetic field. So if this represents the direction of the current, grab the wire, imagine you're grabbing the wire anyway, and your fingers will naturally curl in the direction of the magnetic field, which means your fingers go around down on the right side and up on the left side. So over here, the direction of the magnetic field due to wire A is into the board. All right, now if this then has a magnetic field at all points along it, there's going to be magnetic field up here into the board, a magnetic field down here into the board. So what we have here is a current carrying wire and an external magnetic field that's caused by this wire over here. What does that mean? That means there's going to be a force. Okay, the force on wire B is going to be given by I, L cross B. The L is the length of wire B, but the magnetic field is the one caused by wire A, and the current here is going to be the current due to B. All right, so there's the equation. Then what's the direction? Well, a cross product tells you the length of B, I, L cross B, B is B sub A, that's into the paper. There's going to be a force on this wire in that direction. So that's the force on B. Now, think about this. Wire B also creates a magnetic field given by this. Wire B also creates a magnetic field over here on wire A. So grab the wire. What does that mean? Over here at wire A, there's a magnetic field line that comes out of the board, and that is B sub B. Okay, at that point then, there's going to be a force on wire A. And it's going to be I sub A times L sub A cross B sub B. All right, now what direction is the force going to be on wire A? Well, once again, I, L, cross B. B is upward in this case, so my thumb points in this direction, and that's F sub A. So in this case, what I have is I have two forces that are opposing each other, and these two wires then are going to be attracted to each other. Now if I take this and I say F sub B, the magnitude of F sub B, is I sub B times L. We're assuming L is the same for both wires, so I'm going to drop the subscript from L, times B sub A. But I know what B sub A is, that's this up here. So let's plug in I sub B L, and that's mu naught I sub A over 2 pi d. Simplifying that, that's mu naught I sub A, I sub B over 2 pi d, and let's stick L out here. If I do the same thing for F sub A, that's going to be I sub A, L, B sub B. And when I reduce it down, guess what? It looks exactly the same. Mu naught I sub A, I sub B over 2 pi d times L. So if I knew what L was, then I could, and I knew what the currents were and the separation, I could solve an equation like this. Or usually the way that it's written is you'll figure out what the force per length is on each wire. The force per length, just divide by L, and it's this part right here. And it's the same on both wires. Mu naught I sub A, I sub B over 2 pi d. So there you've got the force per length on these two wires that are attracted to each other. Okay, that's a significant finding here. We find that wires are going to literally attract each other if they have parallel currents. Okay, but what if they have anti-parallel currents? So the currents are in opposite directions. Well, it doesn't take much effort to think this through. Let's say we reverse the direction of this one, and now it's down in that direction. Well, the magnetic field due to this one is still in the same direction. All right, so the current now is in the opposite direction, so I, L cross B, the force is going to be in that direction. So F sub B changes direction for this wire. What about over here? Well, the current is down this way, so what does that mean? That means over here that suddenly the direction of the magnetic field due to wire B is in the opposite direction now. And what does that mean? I, L cross B, that it experiences a force in this direction. That's F sub A. So if the currents are anti-parallel, then they repel each other. It'll still be the same magnitude because these equations will still work out exactly the same, but instead of them attracting each other, they repel each other. All right, so you can see what happens here. The parallel currents attract each other with this magnitude. The anti-parallel currents will repel each other with the same magnitude. Let's say that I have two wires that we're looking at from the end, and these wires are separated by a distance d, and d is known. This wire has a current coming out of the page. We'll call that current I1. This one has a current going into the page. We'll call that I2. Now each of these two are going to create magnetic fields. So let's say right up here at this point, right about there, I want to know what the magnetic field, the total magnetic field is due to these two current carrying wires. Well, we'll pick that point so that this distance and this distance are the same, which means that we're picking that point also at the right height so that this is a 90-degree angle there. So we've got a right triangle here. This side is D, and this side let's call big R, We'll call that one big R. Now we may not know what big R values are. Let's say we are given I1, we're given I2, and we're given D. All right, but I want to know what is the magnetic field due to each of those at that point. Well, based upon direction arguments here, grab the wire, thumb points in direction of the current. At that point there, B1 is going to be a tangent to the circle, so B1 points in that direction. That's the magnetic field due to wire 1. And then for this wire, grab it, at that point, the B2 is going to point in this direction. Now, you may think that those are exactly the same, but they're not. If I1 and I2 are different quantities, then B1 or B2 may be larger. So let's draw one of these to illustrate that. Perhaps B2 is all the way out there. Then the resultant is going to be, using a parallelogram here, the resultant is going to be that. So that's the total B. And we'll have an angle here. We'll call that angle alpha, just because I got tired of writing theta. All right, so R, let's see, R, we know that R squared plus R squared is equal to D squared. So 2R squared equals D squared. So what is R? It's going to be D squared over, no, it's going to be D, that's D, D over square root of 2, like that. So that's what R is. If we know what D is, we can write R. Then the magnitude of B1 is going to be mu naught I1 over 2 pi R, which is the same as mu naught I1 over 2 pi. Now R is D over square root of 2, so let's put D here and square root of 2 up there, like that. Okay, so that's B1. B2 is going to look similar but not be exactly the same, over 2 pi R, which is mu naught I2 square root of 2 over 2 pi D, like that. Then we want the big B, and we can just use Pythagorean theorem for that. The magnitude of B is going to be the square root of B1 squared plus B2 squared, which is going to be the square root of, let's see, I'm going to have mu naught square root of 2 over 2 pi D, common in both of those, squared times I1 squared plus I2 squared. There. We can, let's see, simplify that by factoring out this portion here. Mu naught square root of 2 over 2 pi D times, let's make that the square root of I1 squared plus I2 squared. So there we've got the magnitude of B. If I were given values for I1 and I2 and D, we should be able to figure this out. In fact, I have a problem with it. That's 15 amps, that's 32 amps, and this is 5.3 centimeters. If we take those values and plug them in here, I've already got this one in my notes. B turns out to be 1.89 times 10 to the negative 4th Tesla. So you can check. Then how do I get this alpha? Well, tangent of alpha is going to be, well, opposite over adjacent. So B1 over B2, which is just going to be, well, let's see, a lot of this stuff is going to cancel. And what am I left with? I'm left with I1 over I2. So it's just the ratio of the currents that gives us this angle then. Then that kind of makes sense if you think about it. If you solve for alpha using our values that I gave up here, it's 25 degrees. Okay, so it's going to be between, if B2 and B1 were exactly the same, meaning that I1 and I2 were exactly the same, then that would be straight up and alpha would be 45 degrees. Okay. If B1 were bigger, alpha would be larger than 45, up to potentially 90. If B2 were bigger, then alpha is going to be less than 45 degrees to potentially 0. All right. So there we've just seen another problem then. There are other examples in the textbook. I encourage you to look at those. In fact, some pretty cool applications there as well. All right, that brings us to Ampere's law, which we will save for next one.